Okay, this next section is on the human eye and vision. So when we're looking at the human eye, here's the cross-sectional of it. So if we start in the back, there's the retina coming around the back. When the image is seen, it is actually flipped upside down. So there's an inverted image of the object. In the back, there's the optic nerve. And as you know from the sectional anatomy, this is the posterior compartment here filled with a jelly-like suspension. One thing I want you to see here is the ligaments that hold the lens in place. And there's the anterior compartment and the iris, which it telescopes to let light in. And you have your cornea on the outside, which is your protective layer. So cornea, like I said, is your protective layer of the eye, and it is translucent. So you have the lens, which is the focusing part of the eye. So it focuses the light to the retina, and the iris is between the cornea and the lens, and it behaves like a diaphragm, controlling the amount of light that is allowed into the eye. So if it's really bright, it's going to cone down real tight, or if it's really dark, it's going to open all the way up. So rods and cones, the roles of the rods and cone cells is to transform light energy into nerve impulses. So that's important that you remember that. This is called photoreceptor transduction. Okay, so the rods in your eye, the average adult contains 120 million rods. They're found in the periphery. They're found in the periphery of the retina, not on the fova centralis or the center of the retina. Low light levels, commonly described as black and white conditions. So it's scotopic vision. Dim objects best viewed peripherally where the rods are concentrated. So the threshold for rod vision is approximately 2 lux. Cones. The average adult has about 6 million cone cells. They're concentrated in the center at the fovea centralis. So they're responsible for the brightness or the colors that we see. They're really good at perceiving small objects better than your rods, and they're photopic vision. So the threshold for cones is approximately 100 lux, and there's 3 specialized forms that are sensitive to blue-green and a yellow-red, and that's important later on. So when we're looking here at this graph, you can see the lux here and the cone threshold and your rod vision with your cone vision here. Just a diagram here again of rods and cones, shows you the general layout. When we are looking at an MRI, this is an MRI sagittal T1 of the eye, you can see a little bit of thickening down here, so your rods are in the periphery and your cones are in the center. So visual acuity, what is that? It's the ability to perceive fine details. So cones are better at small objects. So cones are better at detecting differences in brightness, called contrast perception. So the difference in your levels of contrast are your cones. So they're sensitive to wide ranges of wavelengths of light. In fluoro, we want the highest details. So we want the highest levels of image brightness. So the image intensifier is on modern equipment is in the cone vision region where the visual acuity is at its greatest. So the brightness of the image on a fluoroscopic image, it depends, one, on the anatomy, but it also depends on the kVp and the MA. What we use now is the ABC, which is automatic brightness control, or ABS, automatic brightness stabilization. So those are words that you're going to hear, the ABS or ABC, when we're setting our technical factors to keep the brightness as bright as possible. So high kVp and low MA is also preferred in fluoro. So MA is not given as we use brightness control. So typically we set our kVp. Sometimes we even have kVp variable units also. So automatic brightness control, as we scan the body, it will automatically adjust to keep the brightness at the level that is preferred for our vision. In table 25.1 in Bouchon, so page 405 is a sample of the KVPs that are recommended for use in fluoroscopic imaging. All right, we're going to go into dose now. So we're going to take this a little bit further and we're going to talk about karma, so air karma. Dose, the way we define dose, it means the absorbed radiation as defined by the International Commission on Radiation Units and Measures. So all this information that I'm going to be giving you here is in your web links. You'll see it. It's the va.gov, so it's your FDA recommendations. Okay, so the absorbed dose is the mean energy impacted to matter in units of joules per unit of mass in units of kilograms, where the special name for this unit is absorbed dose, and we call that the gray, so, or the RAD, right? Dose area products, so DAP, you're going to be seeing that come through here and there, so I wanted you to know what it was. Dose area product is known as the karma area product, a measure of dose times the area of skin irradiated. So that's the dose area product, is how much and what is the area that we've covered. So as you recall, the gray is a unit of absorbed dose and also is referred to as karma and is equal to 1 joule per kilogram. Now, they wanted me to talk about this to you. We'll break it down when we actually get to the biological effects, but I kind of wanted you to know how they're talking about things. So they're actually going to bring the karma into this. So what is that? The K is the sum of the initial kinetic energies of all the charged particles liberated by uncharged particles in units of joules and a mass of material expressed in units of kilogram, where a special name for the unit of K is gray. All right, hang in there. When the material is air, the quantity is referred to as air karma. So if I'm talking about Rankine, I'm talking about what comes out of the tube and the dose that comes out of the tube. And we're going to talk about karma. Karma and Rankine go together. So in air karma, you're going to refer to that as Rankine. Okay, so reference point to air karma is quality used to estimate skin dose, where the reference point is expected location of the skin for an average patient. So we're going to cover the FDA also and what they're talking about, along with our syllabus from the state, and we're going to dive deeper into this, but I kind of wanted to introduce the karma to you. There's the karma with absorbed dose, there's the karma in air, so it's a unit of dose. So we're going to go into just review of our basic units. So the Rankine, as you know, is the exposure in air. So breaking it down, it's the exposure out of the tube. So if we talk about the RAD, so the RAD is absorbed dose. So we've talked about that. It's equal to 0.01 joules per kilogram in matter. So 100 rads is 1 gray. And that's how much the patient dose, how much the patient absorbs. So the RAD is how much the patient gets. Whereas the REM is, 1 REM is equal to 10 millisieverts. So the REM and the sievert are units of dose that are used when describing biological effects of radiation, which we've talked about. But this is where the REM is for occupational exposure dose. So our badges, the little jump drives that you guys have now that used to be Landauer, that is measured in REM. So that is occupational dose. So coming out of the tube is Rankine, in the patient is RAD, and to the occupational worker, it's REM. So that's an easy way to remember how all of this works. Now they broke down the sievert a little bit further. So they said that the sievert is the measure of absorbed radiation. However, the sievert is corrected for the carcinogenic risk of the tissue that has been exposed. So the sievert says, okay, what is the carcinogenic risk? So that's measured in sievert. So broken down a little bit further, so the Rankine is beam intensity in the air. So the SI unit is the gray, and 100 R equals 1 gray, or if we say air karma is also. So the RAD is the absorbed dose, so that's what's given to the patient, and the SI is the gray, and 100 RAD equals 1 gray. The REM, and that is what's absorbed in the patient, whereas the REM is our occupational dose. It's measured in the sievert in the SI unit, and 100 REM equals 1 sievert. So the one thing that you probably are seeing a pattern of is 1 Rankine equals 1 RAD equals 1 REM. So keep it simple that way. But if we're going to be converting, you'll want to do these practice problems. You will have a couple on your exam. So you just take the conversions here and put them through here. So I will give you worksheets also in lab to help you calculate some of these. Okay, so that sums up your lecture for your first week, which is very exciting. We have 16 to go. Don't be discouraged. Hang in there with me. All right, see you in lab.